This is the title of a paper of Manjul Barghava, published in the American Math Monthly in 2000. And it's a great read. So I recommend that you go look at that paper. I think he won a prize from the MAA for writing this paper. And subsequently, he won other prizes also. Okay, so there are a bunch of people on Zoom that I know, and so you behave. I'll try. Right. So this is a talk about, well, it's going to start out by integers, but the theory is on a Dedekind domain. So n factorial is a product from 1 to n, and the Bhargava theory of generalized factorials studies them in terms of their prime factorization. So the prime factorization of n factorial, right, is equal to the floor of n over p for the powers of p that divide it, and then you get an extra factor of p when it's p squared. Maybe this was in the Knopfmacher book. Greater than or equal to 1. And this is Legendre's formula. It's also called Dedekind formula. And we have a similar thing for the binomial coefficients. Right, we have A plus L choose L, right, which is K plus L factorial over K factorial times L factorial, which is got a factorization, which so it's beta of KL of P. This we can remove this because all the alpha n's will be 0 from P bigger than n, and will drop out of the infinite product, where P will then be the sum for j greater than or equal to 1 of floor functions minus L e to the j, and you get beta of kn of p is greater than or equal to 0, so k plus L choose L as an integer. And this is true because it's a special case using that formula of the relation that the floor of x plus y is greater than the floor of x plus the floor of y for x, y, and r.
That formula is also true for n equal to 0. I just generalize your result.
That's good. This talk is all about generalizations. So I said, but when you're taking products, it's dangerous to have 0 around. You think you're okay? So I would like to say the goals of the talk, and so I would like to say something about the Bhargava factorial. So he defined, you can find this in a 1996 Krella paper, where he defined factorials for associated to subsets S of a Dedekind ring. And for this talk, I will restrict to Dedekind domains. You can ask me about the subset of a Dedekind ring. Even I will say things for, and then we have this 2000 paper in the monthly, which explains for Z. And then we have a 2009 paper in JAMS, which adds extra parameters. Order H, P orderings, P removed, R removed P orderings. You read this. I'm writing.
Beta K L, and that's K plus L over P to the J.
It certainly is. Ah, you meant that I was claiming this, Henrik was, I was claiming this for K L greater than or equal to 1 and not including K and L equal to 0. Yes. Yes. I gave a practice version of this talk, and I was told to remove all the stuff having to do with the exceptional cases.
Don't confuse this with sieve method.
Yeah, so there's a baby sieve methods hiding in this stuff. Okay, and he defined n factorial sub s. So it's associated to this. We have this Dedekind domain. And we define for S contained in D, we define n factorial of S, and it will be an ideal of D. So his theory is really about ideals. It'll be an integral ideal, and then binomial coefficients a priori will be fractional ideals. And the recipe is it does it in terms of the prime factorization. So if you're given a prime ideal P, he will define a P ordering, which I will do later. He will define a P ordering of this subset S, and from that he will get a set of invariants which you call the P sequence. So I want to say these, so this invariance could be written as W of SPA. So there's a P ordering A, and it will be A naught, A1, A2, which will be elements, and these will be elements of S. So that's your P ordering, and then you will define a thing which will be the prime raised to the power. So this is going to match the P of A sub n of P. So we're going to have an A sub n of S P A. Okay. And then you can define a factorial by multiplying all these things together. This is clear here. Is n equals 1, 2, 3, 4. You will get n factorial of S will be equal to the product of over all the primes raised to the power A to the n of SPA. And his main theorem is going to be, there's many choices in finding A, but they all give the same answer. So the answer then will be A sub n of SP. Where A sub n of SP is some exponent, and it will be a positive integer or it will be plus infinity. If it's plus infinity, we are raising a prime ideal to an infinite power, and that will be 0. The ideal will shrink to be 0. So that will be the convention on that. And then of course, n factorial of S will then be 0 also. And this will occur if you have a.
Sorry, when he's doing it in a number field, what's special about n factorial rather than something else? But
there's an infinite sequence of this invariance. This is the nth invariant.
I'm just saying his formula is for over Z, I understand, but for more general, what are you defining as something S factorial?
This thing on the right-hand side is an ideal of the ring P.
I understand.
There's an infinite number of things in the sum. For all but finitely many, the product will be the full ring. And your question was?
I think you did ask if you can general.
Yeah, you just write a factorial.
Some other idea, but I think n is just simply an index for a sequence.
Yeah,
It is
it's
not a
not-
sequence alpha, so, and that's why it's n. Is it?
Okay, yeah, that's what I was trying to understand. Normally when you generalize the integer n, but you're not, but n is here just a variable.
In this recipe, first you get n factorial,
Okay,
then you get the integer as the ratio of n factorial divided by n minus 1 factorial, which you then prove is an integer ideal and would define your generalized integer. In his recipe, there'll be a generalized integer.
okay.
It doesn't do that in his paper, but I think
Can you define, let's say, I factorial?
It's a base.
there's going to be a question period. That will be, I want to say, he did this stuff 20 years ago. There have been many papers written on it. Since then, at all levels of mathematical things, I don't know everything that's out there, including, this may be an expository talk. What I'm saying might actually be out there. So, okay. Okay, so now to finish this section, the goals are to define these invariants, to define these P sequence invariants for all ideals in the Dedekind domain. Okay, I want to say there's probably a good reason why you did this. Okay, I gave you a definition. So these things are constructed using these P orderings, and he has these modified P orderings, and then you get a modified factorial that add the extra parameters corresponding to the modified P orderings. So I want to define a P sequence invariant, and that will give you, if you like, it'll give you W sub n of S. BA will be equal to P of alpha sub n of S BA. And now you can generalize your factorials to include more than just the prime ideals in the product. You might say, well, why would you want to do this? Well, what happened is in some previous work, I did some examples with integer sequences and factorials with various people. There's some motivation for it. And the formulas for those involved formulas for base P digits of various integers and so on, and functions like that. And once you have a base P, you can do it for any base. So why not do it for any base? And I use this to define a more general factorial where you're stuck in all the bases. Okay. And you will see it because there are slides with the actual numbers at the end of the talk for that particular thing. And then, it was defined in terms of this factorization that you got by this product. And so the issue is, it resembles the Bhargava theory. So I thought, well, it'll just be a special case of the Bhargava theory. But then it turns out apparently you need to generalize the Bhargava theory to include it. And that's what is the purpose of this talk, as far as I know. Okay, so what you get is extra parameters to plug into the Bhargava factorial, and the extra parameter is a set of ideals. A set of ideals inside this ideals of our Dedekind domain. Of the domain. So now you can define an n factorial of S comma T, which is equal to the product, but you would allow the product to run over all the ideals in this set that you decide you're interested in. W sub n of S B, which will be the product of B to the alpha n of SB. And the main theorems in this talk, main theorem underlying the Bhargava theory is the theory that says the answer is independent of the P ordering. The P ordering makes an infinite number of choices. Okay, so in Bhargava's case, the T is P, the set of all prime ideals, of all non-zero prime ideals. of the Dedekind domain. There are two exceptional ideals, which are the zero ideal and the unit ideal. And I want to say there's actually a way to define the, when I said you could do it for all ideals, you can do it for those two also. It's got a trivial definition, and it's either one, the ideals will either be 1 or 0. So I'm going to omit them. Okay. These are the Bhargava factorials. These p orderings are associated with differences, so we will pretend purportedly going to be an infinite sequence, and we pick A0 arbitrarily. And then we recursively pick AN, given that we've already picked A0, A1, AN minus 1. Minimize the number of times P divides the product of AN minus AI. I want to say is some of his constructions are coming from interpolation formulas for polynomials, where it's natural to have these differences. And so order P of A is the maximum of E such that P to the E divides A, which is equal to the maximum of E such that the ideal AD is contained in P to the E. So for a Dedekind domain, contains and divides are equivalent. Yes?
We look at this classical n factorial, but now think about field extension. In your definition over this Dedekind domain, give you the same answer n factorial?
Each of these factorials with a D and an S is a different animal entirely.
So it's not that.
Let me say about Dedekind domains, since this is maybe the standard Dedekind domains that we're interested in: rings of integers of algebraic number fields, or formal power series rings over a field. Okay, double bracket X will come in, but Dedekind domains, so their main property is a unique prime factorization of ideals. Existence and uniqueness of prime factorials of ideals, you assume it's no Noetherian integral domain then.
Understand, yeah, right. But you are defining this sequence.
Okay, so what I do is I pick A equals AN to minimize the power of P that can divide the product. And I want to say this word P of A in this case is an additive valuation. Right, and VP of A plus A2 is greater than or equal to the min of VP of A1, VP of A2. VP of A1, A2 is equal to VP of A1 plus. Okay, this is this Bhargava theory, prime ideal, additive valuation. And when we go to composite ideals, which is the point of the talk, then this stuff will change. Okay, and the main theorem. Okay. So okay, and we call the value you get here W, I forget my notation, W sub n of S P based on my P sequence. Okay, so this will be P to some power, and that power I'm going to call alpha sub n of S P A. This is the value that attains the minimum. Okay, axiom of choice got used here. I don't think so. Okay, so the main theorem of Bhargava is, in this regard, is okay. So this is the P sequence. This selection was a P ordering of A, and these values are the P sequence associated to that ordering. To the ordering. And he started out his first paper using, this is the definition of the P sequence, and by 2009 he switched to the exponent. So the point of the exponent is the exponent always stays inside the integers. It's an integer invariant, whereas this thing depends on whatever Dedekind domain you're in, and it's a confusing object, but these are just numbers. Okay. So the viewpoint is the value. So I'm going to say that the values A sub n of SPA are independent of the choice of the P order.
I'm sure there's other ways of describing it, like Newton polygons and things like that.
I don't think it's Newton polygons, but I will say, if you look at this monthly paper, he says right at the beginning, this is the theorem. Let's derive all the consequences of the theorem. And you're getting a bunch of amazing stuff immediately, not as long as you believe it's a constant. Okay. The proof that it's actually well defined is then postponed way later in the paper. And the reason is eventually he succeeds in deducing enough stuff to identify these invariants Wn of SPA, identify them as some particular things inside a ring with a particular property that has nothing to do with the definition of P sequence. So that proves it's an invariant.
Okay.
Okay. And in his various papers, there are quite a number of different characterizations by this method that are in terms of pure ring theoretic properties of various sorts. Okay. But that's where we're going. The point of this talk is eventually to come back to B and do this thing for the general ideas and explain why there was an issue. But okay, now we can define the factorial. We can define the factorial, which I already did. We can define the binomial coefficients in terms of these factorials by this formula. So now we have the formula again, that P to the alpha sub n of SPA, which is now equal to P of alpha sub SP by the theorem over all the prime P. And of course, one has to prove that all but finitely many vanish and so on. And then if you like, you can get the generalized integer, which will be n factorial divided by n minus 1 factorial after you prove that n minus 1 factorial divides n factorial, so on. So now let's do the general. My notes say I should tell you a few examples. So before I get to that, so here's a theorem of Bhargava. If you take the ring to be Z, the integers, and you take S to be the full set of integers, then the sequence A, which is 0, 1, 2, 3, is the simultaneous P ordering for all the primes P. For all the primes P for the set S for the set S, and you can use this P sequence now This is a P ordering. We use it to compute the P sequence, and the P sequence will turn out to be j equals 1 to infinity of a. I'm not sure I have this right. I'm not going to waste time. I'll just say that n factorial of x is going to be the usual n factorial. I'd also like to note another thing you get out of this is that you get some inclusion relations, which are if S1 is contained in S2, so you change the set on which you're doing it, then you'll have that n factorial of S2 will divide n factorial of S1. So if you make S1 smaller, you make the factorial bigger. And so the maximum size you can make, the minimal size factorial you get is by taking the whole ring. And so for the ring Z, that minimal is the usual factorial. Okay.
How easy are these things to compute? Is there a Stirling type formula? Or?
They are tough. There are a few examples where people can do them, and there are various papers computing them in various ways.
Like an approximation, like a Stirling type formula?
Well, once you vary S, if S is small, the thing can be growing like gangbusters, much faster than n factorial, for example.
Yeah, but I mean, fix S is small.
That's a good question. I don't know the complete answer. I know of papers analyzing the growth rate of these things in specific examples. One of them was posted on the archive in the last 4 days. Probably if you search on the title on Bhargava in the name of the paper, you will spot this paper, and it's trying to do it for interesting examples, but the person is trying to do something exactly like what you asked. Okay. And another theorem is that the binomial coefficients are all integral ideals. This is what happened in practice. Half the talk before we see anything interesting.
Open the whole
Huh? Maybe the other half too. I'm always willing to oblige because, you know, if it isn't up to snuff, it's an encouragement to others. Well, great. Great. Okay, so now let's do the case of arbitrary ideals B. Okay, so we're going to define a B sequence. So we're going to define it almost the same way. For ideals beta not equaling to 0 or D, non-trivial ideas, we define a B ordering the same way. Exactly what you expect. Pick A0 arbitrarily. And now we are going to pick AN to minimize. But now we're going, instead of the product, we're going to use the sum. A equals 0 to n minus 1 of word B, AN minus AI. Where word B, which I will denote V sub B star of A, is again the same thing. The minimum of E such that B to the E divides AR equal to the minimum of E. The max. Is this right? I hope the paper is smarter than I am. Same thing, you have the inclusion relation. Okay. Anyway, VP star is no longer evaluation. It satisfies VP star of A1 plus A2 is bigger than the min of VP star of A1, VP star of A2. But VP star of A1, A2 is greater than or equal to VP star of A1 plus VP. So, and that boils down to the statement that you want to note that ord B of the product of the AN minus the AI is greater than or equal to ord B of the sum of the ord B's of the AN minus AI. And you have equality if it's a prime ideal. Okay, so the original Bhargava invariant doesn't generalize to the does not generalize to the composite ideal cases. You can write down B sequences, two different B sequences that don't give you the same invariance. So that B sequences don't all have the same value. But it turns out the additive ones do. And indeed, in his JAMS paper in 2010, he was stating 2009, he was stating the definitions of these invariants that were in terms of the sum and not the product. But he was only applying them to prime ideals. So at that time. So that means that this the main theorem that we're after, of course, is the well-definedness of these things, which is that for Dedekind domains, values alpha n of SBA for a B sequence are independent of the choice of the B sequence. Okay. So now, once we have this B sequence, we can define factorials for this particular. We can define factorials and generalized binomial coefficients as before. Only we take a product over the particular set of ideals you want to take. The case I'm interested in is where you take all the ideals. So the extreme case, you have the same. We have the same sort of inclusions. I want to say there are now two variables, so we can define n factorial of ST, where this is now going to be a set of integral ideals. So let me just say, if you make S smaller, the factorial gets bigger. If you make T smaller, the factorial gets smaller. And you can, of course, reduce T all the way down to being a single prime ideal. So you, and in Bhargava's paper, he does consider cases where the set S, for example, is all the powers of 2 or whatever. And in that case, really the primes of the 2 don't. Maybe I'm right. So the proof is, maybe you would call it a kludge. So I thought also that perhaps Bhargava's proof should immediately generalize to the composite case, but that doesn't happen. Perhaps the JAMS paper, there's something in there that could cover this case. But what I want to do, I want to do the case for the case Z. Wijit finished his PhD last year, and the case Z is done in one chapter of his PhD thesis. And he found this critical trick, which I'm going to show you. I said, so it's a very simple, nice device, and it will. Since we came to these problems because we were working on this other project that led to discovering these factorials, which is using the base B digit expansion. And this is going, and the motivation kind of for these things was, you've got the base expansion working for all B's, and only base P's show up in the factorial formula. What are all those other bases good for? This is something that's always bugged me in my entire career, that what is the information contained in the other base digit expansions for factorials, right? If it's an operation on the torus, then of course the prime ones of the periodic orbits. Okay. So I'm going to use the base P expansion. Okay. So the idea is we are going to make a map. So we have the ideal B, which is composite, and we want to look at the base B expansion of N. And then we are going to define a map phi B that will map Z into the formal power series ring Z double bracket of T. Okay, by using the base P digits. So I will have N, and it will have an expansion dj B to the J equals 0 to infinity, right? Because we have to use the B-adic expansion. So for negative integers, this will be infinite. So we will get a power series, and we will simply map that to the polynomial f sub n of t, which is equal to the summation of the digits dj t to the j. Okay, so this construction is completely concrete, and of course there's a formula for computing. There's a formula for computing dk of n, which is a over b to n over b to the k minus b times n over b to the k plus 1. So we have a nice recipe for directly computing the digit expansion. Okay, so we get the following lemma, which is the map BB from Z to Z double bracket T, which however is not a Dedekind domain, so fine, we will embed it in its we go from the Dedekind domain to its quotient field. Okay, this is a Dedekind domain. And we are going to use this map to take our B sequence over here and map it to a T sequence on the maximal ideal. And that thing is a prime ideal in this Dedekind domain. So the Bhargava theory applies. And now we show that this completely transports a B sequence into a T sequence over there. And that the point is, it has to be defined for all elements of Z so that it can cover all possible subsets of Z. Okay. Okay. So we have to prove that OR B of A1 minus A2 is equal to OR T of phi B of A1 minus phi B of A2. And we take our set S of A's and we map it to a set U, which is, of course, the phi B of A. So each point will go here. So the map has to be injective. This will be true for all A1 and all A2 in Z, which will certainly, this recipe here will be true for all A1 and A2 in Z. So it will transport the B sequence over here into a T sequence over here for the set U, which is the image of S. This map is injective. Okay, so that does it. That does it. We mapped a B sequence into a T sequence, and the invariants match. Each invariant alpha sub n of S B A will exactly equal alpha n of U V B of S T in my new domain. Now, I should say that all of Bhargava's more complicated invariants, the order H invariants and the R removed invariants involve minimizations, but they all use exactly these quantities to go there. So that the transport of the invariants over there pointwise means that all the other Bhargava invariants will be carried through this map. Okay, so here is the observation, which is why I think this stuff is really amazing. This is a map between two rings, mapping our original Dedekind domain into a power series ring over a field. But this map destroys the ring operations for a composite idea. Either in all cases, it destroys the ring operations. It doesn't preserve either addition or multiplication. Okay, whereas the maps that Bhargava is using for doing the reductions in the order P case, we're using compatible with the ring operations. So that, and I don't know that you're whether or not you can prove these results staying within maps that are within the ring operations. And I'd also like to address Peter's question. Well, maybe so the observation is the VB do not preserve ring addition or ring addition or ring multiplication. I was interested in this example because it carries the invariant. It carries the invariant over. So if you try to do it by localizing at A, then you'll get a semi-local ring. That you want to turn this composite ideal into a prime ideal. So it's pretentious. It's pretending it's a prime ideal. Okay. So there's another place carries over between these rings. Well, there is the Machizuki ABC conjecture proof has this feature that it has methods for inter-universal Teichmüller theory. It's transferring things from one universe to another. Okay. Well, this is a very concrete example where you actually
You realize you're being recorded.
Yes. Well, I mean,
I'm just teasing. Fine.
This example doesn't have anything I mean, I see this as a positive example. This is a positive example showing there are definite situations where you can succeed in transporting stuff from one place to another. That's a bit surprising because you're transporting composite things into prime things. So I think it's and there's no arguing about it. It's I see it as a positive thing towards
So what's our shot? So what's the conclusion? Yeah. So this doesn't preserve this ring operations, but
it carries these invariants A sub n of S VA to this invariant A sub n of U V of U T A. I mean, it's transporting information from one place to another. I mean, you really can do this, and what he's doing in the other situation is also transporting information. It's a much more sophisticated stuff that he's doing.
Based on that formula.
Yeah, this formula right here. But the point is it holds for everything in the full ring.
So, I'm sorry, but what does this count? I mean, the factorial count.
Good question, because I'm going on. Well, let me say I have two things to do. The next part is to show you how you do it for Dedekind domains. And then the third part is to go back and get a proof that proves Bhargava's thing for a formal power series over the field, in which case we get an identification for what the invariant is. It's in a different form than what Bhargava has stated it. I presume it's essentially equivalent. But it's in a better form for an analyst because it's a maxi-min condition. So it's that's what I'm planning to do. Okay, so now I'm in that Dedekind domain case. And we are going to so I will show you what we do. We start with our Dedekind domain. So the problem with the Dedekind domain is when you use a base B expansion, you need to expand in terms of a base. And a base means you need B has to be a principal ideal. But in a Dedekind domain, the ideal class group is in the way. And I wanted to mention Dedekind domains are more complicated than you may think. They can have any cardinality, and the ideal class group can also have any cardinality. It's a theorem that any abelian group whatsoever can occur as the ideal class group of some Dedekind domain. I mean, uncountable, whatever. So here's our Dedekind domain. It's got an ideal class group, but actually there is a result saying you can embed this thing in a larger Dedekind domain of class number 1. There's a larger Dedekind domain that is a principal ideal domain. And this construction is due to Claiborne in 1965. I'm not sure whether it's how his name is pronounced, Claiborne or Claiborne. Someone will have to. Okay, and this construction is kind of functorial. It says we take D and we adjoin an indeterminate and take the polynomial and ring in D, and then we invert a whole lot of polynomials. We invert all the primitive polynomials. So we localize by inverting all the primitive polynomials, which are a sub j of t, j, a sub j equals 1 to n, a sub j, y to the j, where the GCD of the AJs is equal to the unit ideal. Okay. Okay. And what this does on the level of, first of all, it takes the idea. First of all, the theorem is this is a Dedekind domain and it's a PID. But it's better than that. The ideals match 1-to-1. So the ideals that occur over here in this new thing, D prime, there, it's a 1-to-1 onto correspondence. In this injection, the extension map goes and the extension composed of the contraction goes right back to the same ideal. You don't get any new ideals. Okay, so we are in a setup where we have an ideal B and we will inject it into an ideal B prime, and B prime will be a principal ideal, so it will have a generator B prime. Okay, and once we've got it in there, then we can do the B prime digit expansions of all the, we can do it for everything that's in D prime. Okay. So now we can take D prime and we can map it into D prime double bracket T by the B prime digit expansion. By the way, the digit expansion is really a series of higher congruences mod higher powers of B. You don't have to complete or whatever, but you can, anyway, you can prove that the equivalent version of this lemma applies, and then we have to go to if you want to apply Bhargava stuff, you might as well go to the quotient field, K prime of T. So we have this map here. This is a ring homomorphism. You have this map here. It's a ring homomorphism. And then you have this thing. It's not. It's ring operations are not preserved. Okay, so that's the recipe for showing it in the general case. Okay, now I wanted to say one last thing, which is to give, which is the Bhargava thing for the ring R is K double bracket of T. Okay, and I would say this is a condensation of one of his proofs idea. So this ring, I'm okay. This is a Dedekind ring. I form the ring R, which is D, a polynomial ring, and a new indeterminate. So this is K double bracket T. Well, maybe I can use X now. Polynomial ring in X. So here's a polynomial P of xt. Okay. So that now the coefficients are in this. Now the coefficients are coming from this power series ring. So there's Cj to the T, y to the j. So this is j equals 0 to n. This is a two variable polynomial P of xt. And so we will say it's T primitive if the GCD of the Cj of T is K double bracket T. It's equivalent. It says that it's equivalent to saying some Cj of T has a non-zero constant term. Okay, and then the result, the criterion will be for a subset U of K double bracket T alpha, so K of U for this ideal T in double bracket T is given by the maximum over P of YT primitive polynomials of degree K of the min of the ord with respect to T of P of F of T taken over all the F of T that are in U. The point being that the right-hand side is not defined in terms of the T sequence. It's a thing that's defined purely in terms of stuff that's in U, and it has this max min form to trap, which is what traps it. And okay, so to finish, there are three things here. One is the generalization of the invariants, the device that uses these congruents preserving maps to map from one ring to another without doing the ring operations, which I think is a thing possibly of higher utility. I actually think that this Claiborne construction of going to the of going from D to D prime is really interesting. It's getting you class number 1, but D prime modulo the ideals is not a finite set anymore. If you could start with a number field and you would map into this thing, you'd say, hey, I solved the number field problem. I got a class number 1 thing by this thing, but the residue class rings are all now infinite. But it's still really interesting. And the last thing is this max min criterion is sort of a different way to express the variance. Okay, as you said, you can get the integers, the generalized integers, by taking the ratio of 2 consecutive factorials. So these are the generalized integers. Well, the primes just do exactly what the primes are going. The generalized integers for primes are just the primes themselves, but the composite numbers now have bigger powers. So if you look at 1636 to 56, okay. All this, if you see this, it's kind of dreadful, okay? So here are the general factorials, okay? Up to n equals 12, given in factorized form. Not very enlightening. Okay, here's a discussion. First, they are, I didn't have time to do the divisibility sequence, but these, in Bhargava's example, the ordinary factorials, it's the divisibility sequence, the generalized integers, if n divides m, then the generalized integer n divides m. And they respect GCD, but the sequences you get here don't quite respect the GCD. That's a counterexample. And the other thing is they don't appear in the OEIS, the Online Encyclopedia of Integer Sequences, as of yesterday. So I assume they are new because integer sequences that are flying around, people find them and they put them up in OEIS. OEIS gave me 3 sequences that match for the first few terms. And one of them is the product from j equals 1 to n and k equals 1 to n of the GCD of jk. And I bet this the sequence we have is going to divide that. Another one is the determinant of the character table of Sn. I don't know that it divides because I haven't tested the full set of things there, but it certainly divides the first. This thing appears inside the first set of those. Okay, and now you can get the binomial coefficients. So here's a table of part of Pascal's triangle. It still has a symmetry around the middle. It does not have monotonicity. It's not unimodal like the binomial coefficients are. So if you look at row 8, you can see it's not unimodal, and row 10. Okay, nor is it monotonically increasing when you go down columns, as the ordinary binomial coefficients are. So that's some of the things I said here. It's not unimodal, it's not increasing in columns. And the Pascal triangle relation is broken, which says that each thing is the sum of 2 things on the previous row. Maybe it's the sum if you allow weights, rational weights. I would prefer to see rational weights that never involved any denominators bigger than the row they were on. And I'm at this point, I can't tell you whether it's can be done. I could do it by hand for some small ones, but I don't know. And also it's going, those, you can't do the weights, so they behave nicely from one row to the next. So it's an unusual creature. And what was the question? There was one question related to this. Anyway, that's all.